Question number 58. Figure shows two identical parallel plate capacitors connected to a battery through a switch S. Initially, the switch is closed so that the capacitors are completely charged. The switch is now opened and the free space between the plates of the capacitor is filled with a dielectric constant free. Find the ratio of the initial energy stored to the final energy stored in the capacitors. So here, this is capacitor A, this is capacitor B. Both have same capacitances C. When the first case, here it says that initially the switch is closed. When switch is closed, potential difference across both the capacitors are same. Then in this case, energy stored, say it is Ui will be half Cv square plus half Cv square. That is Cv square. Now, when switch S is open, in that case, this will not be connected battery, but this will remain connected. Here, space between the two plates is filled with capacitance K. So here K is K. Now, potential difference across the capacitance A will remain B, whereas potential difference across capacitance B will become V upon K, where K is dielectric constant. So energy stored will be equal to U final will be energy stored in first capacitance, whose capacitance will increase by K times. So half K times Cv square, and for this voltage will become V upon K and capacitance will increase K times. So it will become 1 by 2 K C times V square upon K square, because voltage becomes V upon K, because it is not anymore connected to potential difference or source of voltage. Now, if we simplify, 1K will cancel out and we will get 1 by 2 KCV square times 1 plus 1 upon K square. Now we have to find out the ratio. So UI to UF will be equal to Cv square divided by half K times Cv square times 1 plus 1 upon K square, which can be further simplified. So we will get 2K upon 1 plus K square. But in our question, K is given as 3. So we put the values. So it will become 3 to the 6 divided by 1 plus 9. That is 6 by 10, which is equal to 5 by 2. Sorry, which is equal to 3 by 5. Now let's go to next question. Next question says a parallel plate capacitor of plate area A and plate separation D is charged to potential difference of V, and then the battery is disconnected. A slab of dielectric constant K is then inserted between the plates of the capacitor so that the space between the plates is filled. Find the work done on the system in the process of inserting the slab. So here, initial energy, say Ui half Cv square, and capacitance C epsilon naught A upon T. Now, Q equal to Cv. So C is epsilon naught A upon D times V. This is initial case. And when dielectric slab is inserted and battery is removed, in that case, new capacitance C will be epsilon naught A times K divided by D, and voltage will become V, suppose it's V1, so this will become V upon K, where K is dielectric constant. In this case, charge we find So this will be C1, V1. So we can put the value. C1 will be epsilon naught A K times D into voltage will be equal to V upon K. So here we can see that charge remains same. Now we have to find out the work done. For this purpose, we have to find out initial and final energy, and then we will find the difference thereof, and that will be equal to work done. So let's see what is final energy and what is initial energy. So initial energy we have already found as half CV square, and final energy UF will be equal to half C1 V1 square. So 1 by 2, C1 is epsilon naught A K upon D times voltage is V upon K, so V square upon K square. So now work done is equal to change in energy. So change in energy, we can find final energy 1 by 2 epsilon naught A K upon D times V square upon K square minus half CV square. So here 1K will cancel out. So here capacitance, this is also C epsilon naught A upon D. We can write it 1 by 2 C times, or better to write C equal to epsilon naught A upon D, because answer is in terms of epsilon naught A upon D. So let's retain it. So this is 1 by 2 epsilon naught A V square divided by K times D minus half. C is epsilon naught A upon D times V square. Now, if you observe carefully, so 1 by 2 epsilon naught A upon D times V square is common. So we write it here, suppose for W. So 1 by 2 epsilon naught A times V square divided by D, which is common. And then here 1 upon K minus 1. And this is our answer. Thank you for watching.